Let's look at an example of a circular motion, which is a circular motion, vertical circular motion, such as what we see here. Now imagine we hang a stone to a string, and we give it an initial speed here. That means we just give it a slight push. Now if the speed of the stone is high enough, it will actually move up to the top and then come back down again. But if the speed of the stone that we give it here is too low, then it will maybe stop, go up here and then fall back down again, or it may fall up, or will go up here and then it will slack and fall down. So we are talking about the case now where you give it sufficient speed such that it is able to complete one circle. So you give it sufficient speed, it will go very fast at first, it will slow down because of conservation of energy, KE changing to GPE, and then you will accelerate back down here. So you will go fast, then slow down, then go faster, then slow down and then go faster, then slow down and go faster. Alright, so let's talk about this case here. So which means to say the speed here at the bottom is not equals to the speed here. So to solve circular motion questions, there are actually two common ways of solving. The first one is by resolution of forces, which is to examine the forces acting on the object. So let's talk about at the top of the circle here, which is here. Now what are the forces acting on the stone? You will definitely have your weight, mg, and you will definitely have your tension of the string, which is also downwards. So what will happen is the two forces here, which is your mg and your tension, will both add up together to give you your net force or your resultant force. So once again, if you have a resultant force, the question that we need to ask ourselves is, does this resultant force cause a linear motion, that means cause the stone to move downwards, or does it cause a circular motion, which means to say it moves in a one complete circle here? Now since the stone moves in a circle, so therefore this force here, this resultant force here, is actually a special type of resultant force called your centripetal force. So therefore the resultant force here, which is your T plus mg, becomes your centripetal force, which is mv squared over r. Of course, you can also write in terms of mr omega squared if you wanted in omega, but for the purpose of this example, we will use the example mv squared over r. Meaning to say, therefore, if we were to rearrange the formula, bring the weight over, then we get the expression for the tension, which is mv squared over r minus mg. Now, at the bottom of the circle, let's examine here, what are the forces acting? You will still have your weight downwards, but this time the tension acts upwards, because if you tie the stone using a string, as it tries to move, you will feel that the string will pull the stone back upwards. So therefore, you have two forces here, your tension and your weight. So then the question is, which is bigger, tension or weight? Now we can conclude that tension here must be bigger than weight, so that your resultant force is upwards. So then you will get a centripetal force, because centripetal force means a force towards the center of the circle. So if it moves in a circle, then there must be a centripetal force. That means your resultant force must point back to the center of the circle. So we know that tension here is bigger than the weight. So therefore the resultant force will be tension minus weight. And this resultant force causes circular motion, so therefore it is equals to centripetal force. So tension at the bottom is mv squared over r plus mg. But once again, please bear in mind that this speed here and this speed here are not the same. Alright, so therefore if we compare these two equations, we can see that now at which position is your tension the biggest. So we can see that the tension here is the biggest because it's plus mg. So therefore, if you keep swinging it faster and faster, if V actually increases, your tension actually increases. So if you swing it too fast, the tension is too high, the string will snap. And where will the string snap first? At the bottom, because that's where the tension is the biggest. However, where will the tension be the smallest is at the top here, because it is minus mg. So therefore, if you were to slow down the stone, that means you give it a lower speed here such that it has a lower speed here. If the speed here is too low, then mv squared over r minus mg will get a 0. That means if your mv squared over r is smaller or equal to your mg, then what will happen is, what will happen is the tension will become 0, and so therefore your object will fall. Because no tension means the string is slack. So therefore, if the speed is not high enough, it will fall. So let's find out what is this minimum speed here that we need to give the stone so that it will not fall. So using back this same equation, now that your tension is 0, this is at the critical point, then we get 0 equals to mv squared over r minus mg. You'll get the formula v equals to square root gr. So this is the minimum speed at the top of the circle in order for the stone to be able to complete the circle without falling. Now, if we have the speed here as square root gr, what is the speed that we must give the stone here? Because remember, we are going to push and give this stone an initial speed, then it will slow down, then go faster here. So what is this initial speed here? In order for the minimum speed on top to be square root gr. So this one, we can use the conservation of energy. So if we understand that as you move from here to here, you will lose KE, but you will gain GPE. So the formula will be loss in KE equals to gain in GPE. So what is the loss in KE? The KE here minus the KE here. So it's half mv squared at the bottom minus half mv squared at the top. Now most students will just write half mv squared and not the half mv squared minus each other. Now it is important for you to understand that at these 2 points they have KE, so you cannot assume that here has no KE. If this was an example where you threw a ball upwards and it reaches the highest point and it stops momentarily, then it's just half mv squared here. Alright, but because it goes up in the circle, it also has a KE here, so therefore the change in KE or the loss in KE is this half mv squared minus this half mv squared. And that must be equals to mgh, which is 2r here. So it's mg 2r. So it's cancelling the m in each side here, and later on we bring the half v squared over. Alright, and we will be able to substitute the v on top here as this square root gr. Alright, so this v at the top we substitute as square root gr, so you square it, you get gr. And then we'll be able to find the minimum speed at the bottom, which is square root 5 gr. So what is the minimum speed here? Square root 5 gr, in order for it to reach here and have a speed of square root gr, so that the stone can complete the circle and the string will not slack. So these are the two common ways to solve circular motion, which is resolution of forces and also conservation of energy. Now the conservation of energy, we can usually use it for vertical circles, is because you have your change in GPE. But for horizontal circles, we will see that we won't be able to use this. We will use two equations for resolution instead.
That's all for today's video. If you are interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.